Yeah, today I will bring our work regarding some idea of how to design a IoT gateway to be reconfigurable and portable. First of all, IoT gateway is the point of connection between the cloud and IoT devices. A study from the Sensor Growth finds that in all the capital cost of IoT projects, the IoT infrastructure will account for 80% and IoT gateway accounts for 10%. But the gateway is essential to maintain the connectivity of the IoT infrastructure. If lost connectivity, your investment in IoT infrastructure will all in vain. Then in terms of connectivity, if we look into the IoT gateway architecture, there will be two kinds of connectivity. The first is connectivity to the cloud, which is usually a technology that is stable and mature. So research interest is more on the protocol and the traffic flow. What we discussed today is the connectivity with the IoT devices, which is fast evolving. Because they are fast evolving, so we need some design to maintain the software reusability and portability. We can see there's already such modules called hardware abstraction layer in the architecture. Data also backs up the claim of fast-growing IoT connectivity technology. In the table, you can see the most fast-growing ones are the cellular 5G IoT and LPWAN. So the next question is, how can we design the IoT gateway to meet such a trend? Okay. In the market, there are two kinds of solutions. The first solution is based on hardware. The idea is simple, that we can define a universal port to support multiple wireless technology. It's like you can have a 5G card plugged into your laptop and to enjoy the 5G network. Okay. But such solution is limited to the number of ports, and it needs the standardization efforts. The manufacturer should be agreed to accept such a standard. And finally, you still cannot avoid the hardware cost. Yeah. Then the second solution is that we might use the SDR-based solution to this. SDR provides you with the highest configurability, but to master the SDR programming requires a steep learning curve. And also, existing SDR toolchains provide limited portability. The model developed by GNU Radio can be hardly ported to other SDR platforms such as Myriad, RF, and SciPy. In addition, the AI era also witnessed some new opportunities and challenges. We have witnessed the AI processors and the architecture rolled out, and AI algorithm developed for all areas. Then it's the question in front of a gateway designer, how can we leverage and support such trend? Yeah. Today I will introduce our solution to this approach. So we have come from a simple idea. Why we not use a neural network as the middle layer? We built specific modulator implementation on top of neural network. It brings some obvious benefit. The first, such an architecture will natively support AI hardware, such as the GPU and the NPU. Second, because the neural network, we can develop specific functionality in a data-driven manner. Even for a non-expert that not know much about communication, they can still build a working transmitter pipeline. Also, the solution built on such an architecture can maybe easier to synergize with other AI algorithms, such as the pre-processing parts. Yeah. So based on this idea, we proposed our solutions named NN-defined modulator. On the architecture diagram on the left, you can see our system separated into two parts. First, we have a SDR front end, and the second, we have a host devices responsible for computing. The NN model is most on the host device. The host device is usually equipped with the AI processors. And also we have an compiler to abstract the specific processors to support the modulator built in the neural network form. We envision such a new architecture will provide high configurability, user-friendly implementation, high efficiency, and portability. I will elaborate when I'm talking about specific designs. First, let's review some preliminary. What is a modulator? It resides in the physical layer right after the encoder. Under the classic classification, there are two types of modulation, the linear one and the nonlinear one. Today, we are focused on the linear modulation, and the nonlinear modulation is our ongoing and future work. Admittedly, a vanilla neural network still works in a small scale and given enough training time. But such an approach is usually criticized in three areas. The first is such an approach is usually high in complexity, right? Because people usually adopt a very dense, fully connected layer with a large amount of training parameters. But these parameters lack interpretability. You can hardly link the parameters you trained to the classic modulation series. And finally, this is the purely data-driven approach. They are usually affected by the training data you have. Right? If you change a data set and the model fails, you don't even know why. Right? So we think differently. Why not bring the knowledge about modulators into the neural network design? Let me show you what we do. So we start from a study of the mathematics model behind modulators and try to link it to a neural network operations. After that, we study variations in modulation and how can we create a general template. And finally, we study specific wireless technology based on the template we built. We first look at the math model behind the modulation. We employ a classic model called signal space analysis. It links several key components together in a linear way, which is the symbol, the pulse shape, and the signal. Okay. To illustrate, we can take a look at a simple example. Suppose we have a symbol consists of either 0 or 1, right? And we have a pulse shape of a square function. Right? And by multiplying the symbol with the pulse shape, we get the output signal, which is a square wave. Right? We can do this so on and so forth, get a train of a square wave. This is a very simple case of what SSA means. If we look at the neural network, we find a transposed convolution is doing quite similar things. In the transposed convolution, we have the input and the kernel. The output is the input times the kernel. And as the kernel travels along, it multiplies the corresponding input with the kernel to get the whole output. Comparing these two models, we can easily map the input to be the symbol, the kernel to be the pulse shape, output to be the signal, and finally, the stride traveled in each step to the oversample rate. Okay. By that manner, we link the modulation, the neural network with the classic modulation theory. Next, let's take a look at how we deal with variations in modulation scheme. The previous we gave is just a simple case. In real modulation, we have challenges like pulse shape, complex value signals, and multi-carrier modulation. How we deal with that? Due to the time limit, I cannot cover the details, but I put the slides at the end of the talk for Q&A or your later reference. But in a word, if we put all of them together, we can have such a template. It can be separated into two parts. The first part is the transposed convolutional layer that can cover variations in a modulation. And the second part is a fully connected layer that merges the output to a IQ output. Okay. And finally, we adopt such a template to specific wireless technology. Okay. We studied ZigBee and Wi-Fi as the examples. In a nutshell, we adopted the template we just built and try to configure the parameters. We can configure parameters in two ways. First, we can configure them manually, right? Because the model is derived from the modulation theory. Of course, we can derive the parameters also following this manner. But it provides another opportunity. The second opportunity is we can configure the parameters through the training. And that means we can grab the symbol and the signals from ZigBee and Wi-Fi. They are all defined in the specification. Right? We feed them into the template neural network for training. The training result is the parameters we need to configure. Okay. And we can also apply this to a more complex case. For example, in the Wi-Fi, within a frame, it might adopt multiple modulation schemes. Right? We can separate them into multiple segments and train each segment separately and concatenate the output. Okay. And the next question, how do we deal with the portability? Right? And we separate into two parts. In the software part, right, because we are using some very basic neural network model, such as like a transposed convolutional layer and a fully connected layer. They are widely supported for all popular machine learning framework. And the support of the hardware is achieved through the ONNX. ONNX framework is very popular for the portability of neural network among different hardware platforms. In the table, you can see the support of ONNX on multiple hardware platforms. In other words, the portability of workflow is like we develop a modulator as the NN model in PyTorch. Then we export the model to be an ONNX model. Right? The ONNX model will be running and deployable on all hardware platforms as long as they support the ONNX runtime. Right? In this manner, we achieve the portability of the undefined model. And lastly, we take a look at our evaluation performance. And this is our setup. We test on multiple computing platforms and to generate a signal, and the signal can be sent through a lightweight SDR to test its performance over the air. First, we look at the waveform comparison. In the waveform, we can see the generated waveform is quite similar to the standard one. And this also back up to the bit error rate comparison. In the bit error rate, we can see the performance over air also quite similar to the standard one. And next, we look at the portability and efficiency. In terms of portability, right, we can portable among all three platforms, like PC, Jetson Nano, and Raspberry Pi. The solution in the market is the Siona, which is provided by Nvidia. It wants to do the similar things that have the GPU to support the communication digital signal processing, but they are not available to run on Jetson Nano and Raspberry Pi because Nvidia doesn't support. Okay. Also, we can see our performance is running on multiple platforms is also very good compared to the conventional ones. Okay. And we built a demo to show how we can construct a ZigBee and Wi-Fi. And you can see, yeah. This is a test. We use the software to generate a ZigBee, and it can be received by an off-the-shelf ZigBee receiver. And we can do the same thing for Wi-Fi. The receiver side is the Wireshark. It can capture the Wi-Fi signal. Okay. Yeah, in summary, we propose using neural network as the middle layer, and we build a lightweight and model-driven neural network which is interpretable and extensible. And finally, we provide solutions how to port these things among multiple hardwares. Thank you.